Great. Well, Krishna, you made me go through the memory lane now. Since that your Congress that we had in 2005, I was a PhD. 2005 or earlier than that, maybe.
2008, I think. Yeah.
Yes, yes, yes. And it was great to meet you, and we became friends. And it's been great to see you since then. Conference around the world. That's been great. Thank you, and thank you for inviting me, you and the University of Illinois Chicago to do this presentation. Uh, what I'm going to discuss today with you, and thank you everybody for tuning in. I know that it's late in some countries right now. But what I want to do is do a presentation on some topics of course, 1 hour is not going to be enough to discuss everything that we have about final cover systems using geosynthetics. So I'm going to just pick some topics. The way I let's see here. Okay. So the way that I structure this presentation is to go a little bit of definitions and synthetic final cover. And I thought that was a little bit more interesting instead of going heavy on theory, especially since today is a Friday and everybody's tired because we had a long week, to go just on a few case studies, actually two case studies instead of going in a different type of case studies. One about synthetic turf cover, and the other one about an exposed geomembrane cover. So, and I have, I told Professor Reddy, I have 93 slides. Of course, I'm going very quickly on some of them. Most of them are pictures and on the installation of these two type of systems. So I think it will be. I hope it will be interesting and helpful for some of you. So let's start with definition. So let's go to the basics. Definition of final cover. I choose to start with the definition of final cover that we have here in Louisiana, according to our Louisiana regulation. So, and that was written a long time ago. Was written by attorneys, not by engineers. But that's the definition we have here in Louisiana for final covers. Cover material that's applied to minimize the infiltration of precipitation in a facility and revegetated control erosion. So from here, you already see a problem here. There are final covers that you don't need to revegetate it, but that's the definition that we have in our rules here in Louisiana. Now, we have a better definition by Dr. Sharma and Professor Reddy. Final cover is a multi-layer system of various materials which are primarily used to reduce the amount of stormwater that will enter landfill after flow. So very, very straightforward, very easy, and very comprehensive as well. So that's a much better definition that I use now. So when you do a landfill, and I know I'm going very to the basics here. So you excavate your landfill, you put a liner, you put your leachate collection system, you put the waste. You may have a gas system. So most of the landfills here in the United States now have a gas system. And in the end, when you are done with the site or with the cell, you install a final cover. Okay. Now there are different types of final covers. Most common soil covers you see in a lot of different countries is just a low permeability clay cover, and that's it. You don't do anything else. You just put a low permeability clay cover. You can have also evapotranspiration cover. This is more used on locations that are dry. Comes to my mind Arizona here in the United States, where we can use the cover material, the cover layer to store. Use the field capacity of the cover layer to store water and avoid infiltration, and the water it evaporates with time. So and doesn't infiltrate inside the waste mat. And this is good for places that don't have much rainfall, right? Precipitation rainfall. You can have also composite covers. This is one of the most common that is based clay cover, low permeability layer, and HDPE or WLTP geomembrane, a plastic geomembrane. This is the most common one. I'm not going to talk much about composite covers, even if they have geosynthetics. I think that where is getting more in trend right now is use the synthetic covers, which is the main component is a geosynthetic. Some that come in mind, exposed geomembrane, HDPE, or a hybrid that's a synthetic turf cover. And Closure Turf is the brand name of one of the companies that produce this type of synthetic cover. So let's discuss now the difference between the conventional and synthetic cover. So the conventional final cover, you have your waste, you deposited waste, and you have your layer of intermediate cover, 12 inches, 1 foot is about 30 centimeters. Then after you're done with with that location, disposing that location, you install your final cover system. What is the final cover system? Is the compact clay cover. And these numbers, this thickness may vary depending on the location. This is typical here in Louisiana, United States. You put 2 feet or 24 inches, which is about 61 centimeters of a compact clay cover installed in layers or lifts. You may have to put a geomembrane on slopes that are less than 4:1, 4 horizontal to 1 vertical. You put your topsoil, vegetative cover, and you plant grass. Okay, so this is the typical one, the conventional or traditional final cover. Now, the synthetic final cover that is getting more attention, and it has been a few years. This is not a new technology, but I think there are a lot of improvement in these areas, in the synthetic cover or synthetic geomembrane areas that we are using more and more. So you have the waste, we have 12 inches intermediate cover, exactly like that. But instead of construct the compact cover, you can put a synthetic cover here, which can be the artificial turf or exposed geomembrane. And we're going a little more details on how that works. What you can see here, immediately is you have 30 inches, about 90 centimeters of extra space that we could use. So let's discuss a little more in detail this. So some of the advantages of synthetic covers is installation. So as much as sometimes you just need to, you don't have much earthwork for installation of the cover itself, or the final barrier itself, the impermeable barrier, or low permeability barrier. The other thing, as I just said, airspace savings, and this is very important. It says, well, it's just 90 centimeters that I'm going to save, or 2.5 feet that I'm going to save. So, but let's look at a typical 50-acre landfill. When you calculate how much savings you have for those 2.5 feet in these 50 acres and doing the conversions here, this is about 200,000 cubic yards of savings. So it's about 150,000, a little more than 150,000 cubic meters on savings volume. If you use a compaction rate of 1,200 pounds per cubic yard, that's a very conservative one. I mean, if you know what you're doing, you're going to get much higher compaction rate. And tipping fee, which is also conservative here, $40 per ton. There are places here in the United States that you go much higher than that. Probably in some places you go triple that number. That's $4.8 million US dollars on that you save. So it's significant. It's significant. Other advantages have less maintenance, so you don't have soil erosion, you have no mowing, no seeding, reseeding, better water quality from runoff, water that comes from runoff from the site that has synthetic covers is usually much cleaner, has much less contaminants too. The overall cost savings, not only sometimes the installation too, especially for places that don't have inside clays for a final cover, and you have the cost savings on the installation of the final cover, but also you have the cost of less maintenance. That's significant, that you don't have to go and do constant maintenance on your final cap. No, I feel, to be honest, we have to put also the advantage of final covers. One is aesthetics, especially for exposed membranes. If you use black HDP, it's not going to look great in your landfill. It does the work, but you won't look great. The other one is wind uplift. So you have to make sure to find ways to anchor the synthetic cover. It's a relatively recent technology. There is product lifetime concerns. I'm going to go over that in a few minutes. Another thing is the increasing water runoff. You don't have much infiltration, you don't have the field capacity of the soil helping you to retain some of the water. So virtually, or 95%, 95 to close to 100% of the water that precipitates is going to flow, and it has to go somewhere. So you have to account for that in your stormwater drainage. More easily damaged, since some of the synthetic covers are going to be completely exposed. It may be more easily damaged. Leachate seepage more difficult to be detected, is a concern for some people. Installation cost may be higher than traditional covers for some landfills, especially if you have good material on site, inside. It may be the installation cost may be higher than the traditional cover for some landfills. Not always, but it may be. So one question that we always get is, okay, so how long this is going to last? Well, remember that in the United States for subtitle D, you have to make sure that it goes, you keep your final cover for 30 years, okay, at least 30 years. So that's a lifetime that we expect for a final cover. Some of the answers we can find in this white paper number 6 from the Geosynthetic Institute here in the US. And if you go and look at table 6, this is a relatively old document. The original is from 2005. You see that HDP can last 36 years. The double LDP can last 36 years or more. With the caveat, of course, this is for a dry and arid climate. But we haven't seen here in Louisiana surfacing fountains that were lined with HDP. They're older than 30 years, and they are working perfectly. They don't have any problems. We don't see any type of leakages. They have under drain systems that if there is leakage, or leakage detection systems that we can see if there are leakages, they are being working fine, and they are more than 30 years old. So although it's a valid concern, and now you have also, this is a relatively new specification too, from the same Geosynthetic Institute, but this is for extreme HDP geomembranes used in extreme conditions. And this, I think, is about a little more than 1 year old. And the idea of having this specification is that, okay, we have HDP geomembranes that can be used for liners, but we can use the HDP in all system conditions. So this is a way that you can test and give some guidance to manufacturers for using this type of geomembrane, or in this case, HDP. Now, talking about the traditional final covers, the conventional final covers, there are studies that we know that the hydraulic conductivity of compact clay barriers can increase by 3 orders of magnitude. So when you install at 10 minus 7 centimeters per second, maybe after 4 years, and that's what this study shows, the hydraulic conductivity increased to 3 orders of magnitude. It can be 10 minus 4 centimeters per second. So just keep that in mind when you're comparing traditional fiber covers with exposed geomembranes or synthetic geomembranes. And you have this typical case here in Louisiana on Sabine landfill when in 1999 was installed the exposed HDP geomembrane. The installation here was using anchor trench. That's how you anchor that particular geomembrane that site, and still perform as approved final cover. So it's still in good shape. Of course, they need to do some maintenance, but it was installed in 1999, so we have about 27 years that is there. Is pushing close to the 30-year requirement, and it's performing fine. Okay, let's start with our case studies. So the first one I want to show is about the synthetic turf cover, the artificial turf cover that was installed in this facility in Tampahoe Parish of Landfill in 2013. So it's been there for 13 years now. I can't believe that. That was one of the first synthetic turf covers that was installed not only in Louisiana, but in the US. So the facility location is, as you see here, in the south of US, in Louisiana. And one thing that always concerned me at the beginning is that we are very close to the Gulf of Mexico. Well, some people now say Gulf of America. I'll call Gulf of Mexico. And it's a region that's prone to hurricanes. So I said, well, let's see how that works. And so when the manufacturers or the installers come to the landfill trying to sell this solution, I was very skeptical at the beginning, I have to tell. I think intellectual cynicism is good sometimes, and that's how sometimes our critical thinking works. So at first I was skeptical of the solution of using that, especially here in Louisiana, because like I said, it's a region that is very susceptible to hurricanes. But as I went and started studying, I was convinced that it would work fine. And how this system works? You have the intermediate cover, the 12 inches that I showed previously. Then you have the 50 mil double LDPE structure, and this is really your liner here. Okay, so the liner is not the turf. The liner, the barrier is here. Your barrier is here. It's the double LDPE. Then you have the artificial turf with two woven geotextile, and you have sand and fill. Okay, this system is from 2013. They have done a few changes since then. There are other options. You can use now a 40 mil double LDPE. You still can use the 50 mil double LDPE. And instead of a sanding fill that is used for ballast and draining purpose, now they have a proprietary fill. And that's good for locations that don't have a sand pit close by. For this case, on the Tampahoe landfill, we use sandy fill. We had good sand close by on a borough area that attend the specification, so we use the sanding fill. Okay, moving on. So why was this landfill a good candidate for synthetic cover? So there are several reasons for that. They have limited availability of soils for low permeability traditional cover. So all the soils that if you were going to construct traditional cover, you have to import from offsite. That's very costly. Well, it would be very costly. The other is they have port top soils, very low pH soils that would be used for vegetative cover. So in this case, if you have to use the top soils, you have to adjust the pH to be able to grow sand. Steep slopes, 3-to-1 slopes. The facility had a carbon offset gas project. So why this is important? Because they would capture a landfill gas and they would sell carbon credits in the market. And using the synthetic cover, it helped to capture more of the gas that the landfill was producing at that time. And also, they had high cost and difficult maintaining intermediate cover. So everything you put in the slopes would go down the slopes very quickly. They have very difficult keep and cover in the slope. So this is a picture of the landfill before an installation or the slope installation. You can see here, you see very big cracks. Okay, another picture. Very big cracks, a lot of erosion, not much grass going on. This was part of the intermediate cover, and that was in an area that they were not using for years now. And you see here they started placing soil for regrading this location for installation of the cover. So as I said, very very bad situation. They have a lot of compliance issues with the Louisiana Department of Environmental Quality. So, and that area they were not going to use anymore. So said, well, we have to put final cover. We have to do that. So that's how the landfill opt to use a synthetic cover, not only on the because it was one in this case would be cheaper, but not only that because it would be quickly installed as well. So talk a little more about the closure turf project. So the closure of it was just subtitled these cells, which calls cells 10 and 11, for a total of 21 acres. Installation occurred between August and November 2013. We incorporate the existing stormwater and drainage components into closure design. Cementing fill instead of sand on main stormwater drainage components. So we did instead of a sanding fill on locations where we had concentrated stormwater. We use a cementing fill. That's a proprietary product. They now call HydroTurf. That's the product or the component that they call just to be able to keep the infill in the locations that you have concentrated stormwater. Have to think about the gas system design, and I'm going to talk a little bit about that in a minute too. Materials installation cost at that time was 2.2 million. That's only materials installation. That costs CQA or design or any other soft costs. And that was at that time 150,000, represent $105,000 per acre. And the installer the company gave a 30-year warranty period that would cover all the post-closure period for the landfill that they are required to keep it. So here you have a aerial view. So what is here is yellow is the area covered. At that time, they have the active disposal area here. Now they are not using that anymore, but at the time, cell 10 and 11 were the ones that were closed using the artificial turf system. One thing that we really worked on was on the letdowns, the stormwater drainage. That was very important in this case, particular case. You cannot have long distance on the slope for the closure turf. You couldn't have very long distance having sheet flows, so we had to concentrate waters in stormwater letdowns. We had to have bottom anchor trench. So here's a cross section of the system. So we had your 12-inch existing soil cover, closure turf and sanding fill here, and you anchor that at the bottom and also on the top. But here showing a detail of the bottom anchor trench, and we're compact with soil infill. The letdowns were 7 feet wide or 7 to 9 feet wide, depending where they are, and using the hydroturf for the cement binder that I talked to you a few minutes ago. So it didn't need to be very deep. 1 foot was enough, and I mean it's there till today. It works great. It works really great. It's taking the locations where we're going to install the turf. So this was the limit of the location. Here you see already taking shape. Here you can see where a letdown would be located. And starting to fill the area, grade the area for installation of cup cover. One thing is we have to have very smooth area. So things like this, remove all debris, or like this that you have roots there. All these type of debris have to be removed first before you installing the turf itself or installing the system itself. So this is the LDP, WLDP. That's the bottom component of the closure turf before you put the turf on top. Here already another view, side view. You see here being temporarily secured with sandbags. Here you see a component of the stormwater drainage that was already shaped, create this type of berms, diversion berms for stormwater. Another view. Here is, you see the installers welding two panels of the WLDP geomembrane. And here's a detail of the quality control. We took samples and we test in the lab of the panels, and you see here all the information where it was located. I mean, everything was very traceable. We have the date, we have the numbering, we have what location it came, where it's going, if it's going to the lab or it's going to be in archive. Took samples of that to bring to our office, and I believe it's there until today, just to have those in archive. Here is a detail of the anchor trench at the bottom, stormwater drainage system. And this is an aerial picture of, you see here the double DPE. So there was a crew that was doing the double LDPE and another crew that came behind and installed the turf. And it's funny, I mean, this was 2013, so we didn't have drones like we have today. So this aerial view I take from a plane, airplane. It's just funny that in 13 years, the way we do things today is easier. We go there, fly a drone, and we take pictures. That time was not that easy. You have to go with an airplane. It's just funny how in 13 years things changed so much. So here they swing two panels of the turf and put arranging that and putting in place. You see a very it was a very manual job on that, just push and pull and place uh, the artificial turf, the turf component. It's a view here on the slope. That was the north slope of the landfill. And this is another picture, uh, still not complete. You have cell 10 here, cell 11 here, and they are almost completing. I think this is the location where they stopped, the closure turf stopped, or I think no, I'm sorry, they went all the way here. These areas have been already closed, and you see that they had problems here, revegetating. But it is interesting. They had actually the earthwork, the grading of the landfill itself, the landfill personnel that was doing. Then you have the crew that was installed at the WLDP and the crew that came behind and installed the turf. And there is another crew that installed the sand itself. Another picture. So one thing that was important here that they used the closure turf that has very good aesthetics is that if you see here, this is the entrance of the landfill. And we cannot see here, but there is a road that comes all the way here that pass. Of course, people pass there. So it was important to have some kind of good aesthetic. So in the front of the landfill, when you enter a landfill and you see good aesthetics is always one of the first impressions that you get from the site. So here's a view. It still has the sandbags here. It was not removed. It didn't have the sanding fill ballast yet, but you see very nice, very nice look for sure. Then you have infill sand. So this was the way they deployed the sand, and they would come and literally brush into place. And believe it or not, they would come and we would make sure that you have, I can't remember if it was half an inch, I think half to 0.75 inches. And we measure in several locations if the infill was in place as it should. Here's a picture of the cement binder that they put on some of the where they have stormwater being concentrated. And another picture showing the overall slope, north slope. We had several of those already there in the landfill at the time. So this is something that you have to look close whenever you're installing. In this particular case, you have like a little gap here, but this is important. This is a detail, but it is important. You have, it can be a problem if you have, sometimes the air gets trapped inside and it may lift up your geomembrane. So small things like that, we took a closer look during CQA. We were doing the CQA for this project as well, so we're not only the designers, but the CQA company. And yeah, so you said, well, this could be better, and things like these too. Places we always know that we have defects that have to be corrected. We note with little pink flags. Okay, so this is the case for the closure turf. Let me go. It's the same location. This time we're going to use the exposed geomembrane. So this case is from 2022. And these other cells that were closed, which was cell 12, is much more recently than using exposed geomembrane. So in the case that of the texture or the exposed geomembrane, one of the things is exactly the same thing. You have the existing soil cover, but you have the exposed geomembrane here, and you don't have the turf on top, not only have the turf, you don't have the infill on top. So this can be a problem for suction purpose, or it makes it easier for wind uplift. And I'm going to explain this in a little bit. But in this case, you have to have a way to have this anchored, and it can be through anchor trench. In this case, was used like earth anchors, like this. So just to keep that in place. A picture of the location, cell 12. It doesn't look much better than the other ones that we see. Had the same problem, very bad soil, very erodible soils. Here is another look, and here you can see the previous installed artificial turf, and this is going to be installed with another method. So we had to think about ways to tie in both locations too, and we did that. Some of the specifics of the exposed geomembrane and final cover project for cell 12 that was done in 2022. We used exposed geomembrane. Those are just one cell 12, but the area of 23 acres, 1 million square foot. Installation mainly occurred between April and September 2022. In this case, we have to use pressure relief valve. So it's a way that if gas accumulates beneath below the geomembrane, we could use these valves that would open if it has excessive accumulation of gas beneath that, so we don't have a kind of a balloon, if you will. Material installation cost was $2.1 million, so close to $91,300 US dollars per acre. They offer the installers offer a 20-year warranty period, and we discussed this with the parish. It says, listen, they won't cover the 30-year. Now I know that they are doing that more and more since we have better resins or fabrication manufacturing specifications for that. But just because they give a 20-year period doesn't mean that it will everything is going to fail on the year 20 plus 1 day. It's not the way it works. It's just they offer for that, and we believe that it's going to be stayed there for at least for the 30-year period. In this case, a lot of earth anchors were using 6,153 earth anchors, so it was a big project. We have incorporation of stormwater drainage components into the closure design, and also we had incorporation of existing gas system components in the closure design. So we had already a gas system there that we had to take in account. Remember, we installed earth anchors, and you don't want to puncture those the gas system that's underneath the surface. So this is the area that was used to close with the exposed geomembrane. You have cell 10, 11 that was previously closed with the closure turf, and have cell 12 that's exposed geomembrane. So our role in project, we did pretty much from project management to evaluate alternatives for final cover, all the way to engineering certification report that go to DEQ. So that was my company, role on that. Some design considerations on the exposed geomembrane. One is weathering, wind uplift, and the stability in the slope, anchors pull out resistance. So that's things that we had to take a closer look and start seeing how we design that. Now, I promise you guys that I don't want to go very much in detail on this, but I just want you to think about that. So the way we have to think how many anchors we're going to need. So the way we have to do that is to calculate what's the negative pressure that is affecting, that it may cause wind uplift. So in this case, we use this. I call conventional now because there are other ways to calculate that. But that was the conventional method that we used, the Thornberg and Professor Gilles from 1997. So if you have the wind velocity, if you have the wind blowing in the direction of the turf and have it stays there, that's fine. But the problem is, if you have the wind in the opposite direction, you may create a negative pressure, which is the effective suction. And that can cause wind uplift of the geomembrane. So how you calculate this effective suction? So according to Zornberg rule, you use a suction factor. I'm going to tell that in a minute. The velocity, the wind velocity, and you can get that. There are several ways to get that. One way is to get from a specific guidance from ASCE or ASTM. In this case, we used wind velocity of 95 miles per hour. And you may want to discount, if you don't want to be extra conservative, you can want to distract the weight of the geomembrane. So this 9.81, the mass per unit area of geomembrane times the mass per unit area of geomembrane is the weight of the geomembrane, okay, or the pressure that the weight of the membrane causes. So you may want to discount that. Is not much. It's not going to be much. But if you don't want to be extra conservative, like you say, you can discount that. And Z is the site elevation, okay? So, as I said, where the suction factor comes from. So, when you doing this wind uplift design or calculate the wind uplift, according to the methodology, you can have different types. So, types of lambda or the suction factor. So at the lowest point is going to not be much. When you get close, it's going to be higher when you get close to the top of the slope. So the uplift, and this is more, I think that's common sense. You think that you have more wind, you can cause more wind uplift of geomembrane at the top than at the bottom. And that's what this represents. That's the lambda suction or the lambda factors represents, okay? So once we calculate the SE, the effective suction, we have to know the ultimate load of the anchors, and that we can do from a few tests that we do before we do our design. We did several before I start designing. We did some factors and try to come with the ultimate load of the anchors. You have your safety factor that you use, and then you can calculate the number of anchors required divided by the area in a certain area. So it's pretty straightforward. In this particular case, we have anchor space up between 11 and 15 foot typical. So on the top slope, you have typical space of 11 feet, and the bottom third you have 15. So this is important. This is very important that you calculate this and try not to be very extremely conservative, because although you want to be conservative in this case because of the critical location where it's located, and of course you don't want to risk your reputation, but you don't want to be extremely conservative to the point that it makes the project unfeasible. So in this case, you have to be very careful on the anchor space calculations, because the cost of anchors is the materials installation is about 50% of the total. So it's very important that. One other problem that we had, remember, we had gas system underneath the surface. We have pipes all over. And good thing in this case, we knew where they were. So we have very good information, we have very good records. So we could locate our anchors in a way that would not puncture when you do puncture the 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 gas system, the gas pipes. So when you say, well, it's not. This is show just the locations of the anchors in a grid, but it's not a grid because you have your pipes here. See, here's the location where you see this empty space here. This is a gas system pipe location. You have the same here. You have the same here. So you have to work around it. And I have to be very proud that we didn't puncture one. I mean, that was fantastic. 6,000 anchors, and we didn't had any problems with any of that. That was, to me, I couldn't believe when we had that. So installation considerations: earthworks, upgrade preparation, HDP geomembrane deployment, anchor trench, general anchor and patch installation, and also the stability in the slope. You're showing doing grading of the slope. You're preparing the anchor trench, or top anchor trench. Aerial view. In this case, we were using a drone already. It's 2022. You see here smoothing out, grading the site prior to installation. You see here already installing the HDP at the slopes. And of course, you see here someone installer work on a boot installation. Every location was field surveyed. So we marked that in the field where the anchors are going to be. This is a picture of the anchor. So we use their platypus precursor-driven earth anchors, PEAD. So they have like a head design that you to help the installation, and you also have those tendons that I think those were like 6 feet in length, and it was very difficult to install that. So what you do, you punch in basically using an electrical demolition hammer. You puncture, you push the anchor inside, and this takes some time. But I mean, we could install close to 150 anchors per day this way. So you installed that. Here's a picture of an anchor that has been installed. You see here around that location with the tender sticking out the hole. Once the anchor is driven to waste, then the installer uses this hydraulic not the hydraulic hammer, but this hydraulic tool to be able to tension the hydraulic pump. I'm sorry, the hydraulic pump to be able to tension the anchor tendon, and then it's clamped. And we pressure test them. We pull it. We measure how much was tension. And of course, we have that information in spreadsheets and in the field, but we put also the same information: how long is the number of the anchor, the location, how much we pull, their starting depth. That was important. In this case, the start anchor depth was 34 inches. It shows here. So all this is after you put the installed anchor, you had to cover, and we outstrewed that with a piece of the HDP. Same problem we had.
No, I meant for the bollards. Like if I delete a bollard, do you want me to?
We have the boots here, boots for the installation. This is a gas pressure relief valve. That also the same thing. You have to put boots around. One thing that makes me very nervous is how steep was the slope, and this is always a concern when you have several clues. I mean, those are 3-to-1 slopes. It doesn't look in this picture, but they are very steep. And of course, you have people there working, and you don't want to have accidents. That the main thing is have everybody safe. Uh, One of the things that the installer wants to do is to work through the night, just to be able to attend the deadlines. And so they have 24-hour work there. So we have 3 crews work 8 hours each. That helped with the wrinkle control too. It was not intended to that, but that helped a lot. And I imagine that our people on CQA would not like that. They love it. They love to work during the night. Was colder, was quieter, and they did very good job in that. Of course, you have to adapt the tools to be able to have good lighting. And this is a final picture um, of the slope after install the HDP. You can see here the locations of the anchors. Another picture of the slope and the area, the cell 12 that was closed. We're doing also a stormwater quality research activity that we collect and compare stormwater samples from 3 areas. One in the closure turf with the one with the exposed geomembrane, and one from an area that intermediate cover, and you do analysis for all the parameters that are required to monitor for discharge. And what we're seeing is pretty much what would you think is that you have much less turbidity and much less DSS in the areas that have come with artificial turf and exposed geomembrane, and those are way below the water quality discharge limit. Okay, and that's it, Reddy, Professor Reddy.
Very
I
good,
think
very good.
yes,
Excellent.
that's what I have to show to you guys. Thank you very much. I really appreciate, and
Yeah,
I
very,
close to the
very,
end.
yeah,
Yeah, want to ask
very,
questions?
very nice, very nice. I mean, it's an eye opener for all the researchers, in terms of seeing what goes on in the real world. It's not
Yes.
just doing some lab research or modeling or, so what it takes to get things done in the field, it's amazing. So, excellent.